Alright guys, we're going to get started. So James is going to give us the first of two lectures introducing the category theory and then the definition of the topos. James.
Thank you. Yeah, as Dan said, I'm going to be giving the definition of a topos. So let me start out by writing that out. So a topos is a Cartesian closed category with all finite limits and a subobject classifier. So the purpose of the next two lectures is to explain what all of the words in this sentence mean. But to start out, what I'm going to do is give you two sort of relatively simple examples. So the first is just the category of sets, which we've already seen. So that's with the objects being sets and the morphisms being functions between those sets. The second example, which is a little more interesting, is for any small category. The category is called sets C op or set C op. And what that notation means is it's the objects are contravariant functors from, let me actually write it out. So they're contravariant functors from C to set, and the morphisms are natural transformations between those functors. For those who haven't seen the word contravariant, what it basically means is a functor, if you remember, sends an arrow that goes from x to y to an arrow in the second category that goes from fx to fy. Well, a contravariant functor reverses the direction of the arrow instead. So it would go from fy to fx. Cool. This category, by the way, is often called the category of pre-sheaves. All right. So with some examples out of the way, I guess I will move on to the first part, which is discussing what finite limits are. So I'll begin with a sort of motivating example of this. So recall the definition where A and B are sets. Then their product is defined as the set of ordered pairs, such that A is an element of A and B is an element of B. Now, we would like to be able to realize this definition through the language of category theory, but of course, there's a bit of a problem with the way this definition is written, in that as far as the category of sets is concerned, the objects don't have any internal structure. They don't have elements. Or rather, the category can't see that they have elements. So we can't make a definition of a product that has any reference to elements of the objects. Instead, we need to be able to frame the definition entirely in terms of objects and morphisms, because that's the only thing that the category can actually see. So the way that we do this is through the use of universal properties. So let's write out what the categorical definition of a product is. Be a category. The product, and also A and B are elements of C. The product of A and B, if it exists, is an object, which is usually denoted by A cross B. Two morphisms. Pi A, which goes from A cross B to A, and pi B, which goes from A cross B to B. Of course, in sets, these are just the familiar projection maps, such that for any object X in C, and any two morphisms row A, which goes from X to A, row B, which goes from X to B. So given such an object and two morphisms, there exists a unique map theta, which goes from X to A times B, such that the diagram on the right commutes. And the diagram looks like this. So you have X, you have map theta, this is the product here, you have pi A here, actually let's put pi B there, pi B there.
James, the exclamation mark looks a bit like a long apostrophe. So important.
Yeah, okay. It is very important that the map theta is unique. Thanks. Pi A, that's B, and then that's row B, and that's row A. So, a couple of comments on this definition. First things first, for an arbitrary category, it's not necessarily the case that products exist. However, at least for the two examples of categories I gave up here, it is the case that they always exist. Secondly, once you know that the product exists, the fact that this morphism is unique also guarantees that the product of two objects will be unique, which means that this use of the word the is actually reasonably well justified. There is only one product up to unique isomorphism of a pair of objects. Cool. And that's a nice exercise to actually check that, but I won't go through the details now.
James, you said that your second example, all products exist in that category.
Yep.
What are those products?
Products are just pointwise, right? Let me see if I can remember exactly what the definition of pointwise products is. So basically, the product of two functors. So if you want to take, that's just defined as FA times GA.
That's a general story. So any limits or colimits that exist in sets, which is all of them, will exist in that category as a given point.
All right.
Notably, when we get to the definition of exponentials later on, that doesn't carry over. So exponentials you can't construct pointwise because there isn't an obvious way to do that. But I won't go into any detail on that. All right. Let's do another example, which we're going to need, which is pullbacks. So let C be a category as before, and let F A to C and G, B to C, B morphisms in the category C. The pullback of F and G, again, if it exists, is, so first of all, it's an object. Which is usually denoted as A and times subscript C, B. This is admittedly fairly poor notation because it doesn't actually have any reference to the maps F and G inside of it, but usually when you're working with pullbacks, the maps F and G are understood and not varying. So 2. So a pair of morphisms, which I'll call pi A and pi B again, that go from A to A, and pi B goes from pullback to B, such that following diagram commutes. So we want A here, B here, C here, and A to C is F, B to C is G, this is pi A, and this is pi B, such that diagram commutes. Such that given any object X and any morphisms row A goes from X to A, row B goes from X to B. So given any two morphisms such that the analogous square commutes, so I won't write the square, I'll just write what that actually is. It's so G such that G followed by row B is equal to F following pi A, row A. So given any object and any two morphisms satisfying that property, there exists once again a unique theta which goes from X to the pullback. So such that the diagram on the right commutes. So this diagram is, so we've got X there, we have the pullback here, we have A there, we have B there, we have C there. That's G. That maps F. This is pi A. This is pi B. This map here is theta. And X also has maps row A and row B. Cool, that's the definition of a pullback. Once again, does not necessarily exist, but if it does exist, then it will be unique up to unique isomorphism.
Your notation is very suggestive. Your notation to the object in particular is very suggestive. Is there some relationship between this and the product?
Yes, it's a subset of the product, which I'm about to write down. Or at least in set, it's a subset of the product. I should put the other board up first, though.
I thought you were going to complain that the notation for the object is actually an abuse, right? It's a pullback of a pair of morphisms.
Yeah, but I was already sufficiently annoyed with that to flag it ahead of time.
Sorry to put you on the spot, but is the pullback in general a sub-object of the product?
I don't know, but maybe.
Yeah, I don't know either.
Yeah.
Why is it subobject?
So that's going to come later. I kind of skipped ahead.
So again, in category theory, you can't talk about subobjects as just being a subset of the elements, right? So the way that you do it is the familiar abuse where you identify injective maps with subobjects. And so you say that a subobject in a category is a monomorphism. But even that's not quite right, because then you would be identifying, for example, maybe I don't want to go into too much detail about this, but for example, so let's say X is a set, and let's say you take a two-element subset of that set, and you want to call that a subobject. Well, you could send the set 1, 2 to the two elements that you want to pick out. But then you could also send out, say, the set 3, 4, and send it to the same two objects. But you don't want those to be different subobjects, right? Because they're referring to the same two objects. So what you have to do is take an equivalence relation on the set of monomorphisms.
Yeah, so to answer your question also, there's always a morphism, the two maps pi A and pi B there, the universal property of the product, that'll induce a map from the pullback to A cross B. And then there's an exercise to check that's a monomorphism. That's actually from the uniqueness of theta. You can see that's the case.
Where was I? Oh yeah, that's right, the pullback in set. So in set, we have well, that turns out to be the set, it's a subset of the product, so AB in A times B, such that the images under the maps F and G of the two elements in the pair are equal. So such that FA is equal to GB. One other important special case that will come up later when we talk about subobject classifiers is the particular case where, let's say, A is a subset of C and F is the inclusion. So if A is a subset of B and F, sorry, not a subset of B, subset of C, and F is the inclusion, then it turns out that this just collapses to the preimage. So it will be the preimage under G. That's not right, not the preimage of C, the preimage of A. Cool. Any questions about that? Okay, so we could then go on to define equalizers in much the same way, but we've only done 2 of these and it's already gotten a little bit tedious. So instead, what we will do is figure out how to carry out such a construction in general. And the way that we do that is through the definition of something called a cone, and then further the definition of something called a limit. So let's look at what the definition of the pullback had in common with the product. In both cases, we started with some small diagram. Then we asserted the existence of some object, in this case, this guy, together with maps into each of the other guys in the diagram. You may argue that I didn't actually specify a map into C, but of course I didn't need to, because if I assert a map into C, that's the same. It must be by commutativity of the diagram equal to these two. So once I've specified what this guy and this guy is, there's no need to specify what the diagonal one is. Okay, so we specify morphisms out of the object we've defined into each of the nodes of the diagram. And then we further assert that given any other such object with maps into the diagram, it must necessarily factor through this one uniquely. So we want to generalize that. So we're going to define a diagram in a category. So let's start with, let C be a category as before. And let J be a small index category. The word index here doesn't really mean anything. It's similar to how you call it sets. Some sets are called index sets. It's just a way of keeping track of data. So let J be a small category. A diagram in C of shape J is defined as a functor which I'm going to denote just regular uppercase J, going from curly J to C. So that's what I'm going to define a diagram as, and when you see that the first time, it might not be apparent why you would want to define such a thing as a diagram. So let's go through a very simple example. Let's say that J be the following category. It's got 3 objects and 2 morphisms, F and G. Obviously, it also has identity morphisms, but I'm not going to bother drawing those. Okay, so then what is a functor that goes from J to C? Well, it consists of the data of 3 choices of objects, and we can choose them to be whatever we like. So Jx, Jy, and Jz. And then 2 choices of morphisms, because again, you don't have any choices over where you set the identity, so we may as well not worry about them. So that's going to be a morphism called Jf, Jg. And that's exactly what a diagram is, right? It's a choice of a bunch of objects and a bunch of morphisms. The only other thing that we would want our diagrams to satisfy is commutativity. So given any square or triangle or whatever, we want to make sure that the tracing along 2 sides of the polygon agree. But that's exactly what the condition of J being a functor says. It says that necessarily the composite, or the functor applied to the composite, is the same thing as the composite of the functors, which is exactly what the condition of commutativity of the diagram is saying. You're looking troubled, Will.
Well, I can't really see it here, but we don't have vectors.
Well, yeah, this is actually a bad example because there aren't any triangles here. Yeah. I mean, other than the ones that involve identities. So let's actually do it with, if you swap this arrow around, I think it's a bit clearer. So that's F. That's now JF. And let's say you had another map that went there. Well, you do. It's well, you have a map there that's F after G. Well, then necessarily the fact that this is a functor means that this must be the same thing as, so J FOG must be equal to JF followed by JJ, and that's what the commutativity says. Cool.
So could you go over again how you get, I'm not sure how the fancy J is a small category. Is it just?
So J is literally just these 3 objects and these well, 3 morphisms now, together with identity morphism, right? That's a small category. Because the HOM sets, well, because the set of objects is actually a set, in fact it's a finite set, and the set of morphisms is also finite. I feel like, was that what your issue was with?
One way to see immediately that's a category is it's actually a poset. It's a partially ordered set with 3 elements. Sure.
What's the order?
Order defined by the arrows.
Yeah.
Z is less than X. Y is less than Z.
So in general, I think you're probably getting at Sam, but if you start with some diagram, you've got to add in extra arrows to turn it into a category. It's not for free. In this case, you just need to add 1.
You could add more than 1, but you don't necessarily need to add more than 1. Because you could assert, for example, that, well, no, I guess in this case, no, you can, no, my comment was vacuous, never mind. I was thinking of the case where you have a category where it's something like X, and then you have a map that's not the identity, that's F. Then you could assert that FF is the identity, or you could assert that F cubed is the identity, but you need not do any of those. You could just assert that it's an infinite chain of maps.
Interesting exercise. What's the limit of that diagram? It's a good one to test. I don't need to talk about it.
Okay.
Something for the audience to ponder.
Let's put that up now. All right. So suppose we have a diagram. A cone over J is, first things first, it's an object. Which I'm going to denote C. And then it's a collection of morphisms. So for each object X in J, we assert the data of the cone contains a morphism, which I will denote alpha X, which goes from C to JX. And so that's a morphism in C. Such that for each morphism X to Y, again in J, the following commutes. And this is a diagram in C. The diagram is, so we want C here, that's alpha X, so it goes to JX, this is JY, that's alpha Y, and this map here is JF. I'm just going to let that definition sit for a moment and write down the definition of a limit, and then I'll justify exactly what the definition of a cone is saying.
Down just this.
cone, C together with the maps alpha x is a or is the limit of J if I don't know the word for there. If any other cone C prime pi x prime factors uniquely through C. So what does that concretely mean? It means that there exists a unique map theta which goes from C prime to C. Such that for every object in J, so it's C prime, that's C, that's pi prime x, that's pi x, and that's theta, and that's Jx. Notice, by the way, that we're saying that the same theta works for every x. We're not saying that there's a different theta for each x. Okay. So in order to sort of illustrate exactly what these two definitions mean, let's work through the example of the diagram that I had before. So, oh yeah, thanks.
Can I ask actually, when you defined diagram earlier, didn't you define it in such a way that every diagram can use?
Yes.
So is this language of saying such that a diagram can use like redundant in a sense, or is it? Like, is there
No, because here I'm using the informal version of diagram, right? So the
Oh yeah. So
If you say it is a diagram, is that like a clean sentence?
well, it's
I think if you're using it in the functorials, in the sense of the functor, then it automatically computes by definition,
not
right?
every occurrence of diagram in his speech in the last 5 minutes. Is the diagram J.
Yeah.
See, so
Do you
some of the diagrams that commute are the things that live in C, which are the image of J. But this diagram is not one of those, right? Because C and C prime are not in the diagram J.
Okay, yeah.
Also, like a kind of similar question is that the small category J, let's say just for the purpose of this seminar, is that like is it always finite number of sets?
At least for the ones I'm going to be talking about, it's just a finite number of nodes and morphisms, finite number of objects and morphisms.
Okay, so it's safe to just imagine it is a graph.
Yes. So
It's always fun to imagine it's a graph, but finite is not necessary. I mean, for example, inverse and direct limits, which come up very commonly, are infinite diagrams. So it's very common to encounter infinite diagrams, and that's genuinely something you can't get just using finite diagrams.
Okay.
But you're safe to assume it's a graph.
luckily for us, if you remember the definition of topos that I wrote at the very beginning, it asserted the existence of finite limits. So at least for the ones we care about, we only care about finite graphs.
That's right. The sufficiency of caring about graphs is sort of
Example, let J be again X, Y, Z, F, and G. A cone in C over, no, sorry, I need to define the diagram first, don't I? And let J diagram. So a cone over J is going to be the existence of an object, C, together with morphisms into Jx, Jy, and Jz. But again, similar to the comment I made before about the pullback, we don't need to actually bother specifying the morphism Jz because it's going to be fixed by our choices of this map and this map. So this one here is going to be alpha y. This is going to be alpha x. This map here is going to be jg. Oh, I've swapped the roles of x and y. I shouldn't do that. So then now this is going to be alpha y. This is going to be alpha x. This is going to be jf, and this is going to be jg. That's what a cone is. No, I'm going to go on another board. I don't have enough space. How do I want to say that? If cone C prime alpha x prime replaced by x, there exists a unique theta C prime to C such that this diagram commutes. So it's going to be C prime theta C this is x, this is y, and this is, wait, no, it's jx, jy, and jz. And that's jf, that's jg, that's alpha x, that's alpha y, that's alpha prime y, and this is alpha prime x. In other words, the limit of this, well, the limit of this diagram is exactly the pullback of jf and jg. Similarly, the product is the limit of so it's the limit of the diagram that has two objects, x and y, and no non-identity morphisms between them. Actually, let me just write another one is equalizers, which I didn't define before, but it's the limit of a small diagram. So it's two objects, x and y, and a pair of parallel arrows between them.
Sorry, James, you're claiming that you said that that cone is the limit if any other cone is C prime alpha x prime x, or you see any theta.
Yeah.
Such that that diagram commutes, right?
Yeah.
Yeah, maybe not commute.
Oh yeah, I keep forgetting. Such that commutes. This is why whenever I try and write it out properly, I always write such that the below diagram commutes, because that way you can't forget the word commutes at the end. Anyway.
And then you put the diagram on the side.
Well, yeah. Another example, which is very important for what we're going to be talking about with subobject classifiers, is the terminal object. So it's the limit of the empty diagram. So what concretely does that mean? It means, i.e., an object, which is usually denoted by 1, often blackboard bold 1. An object 1, such that for all C in C, on the set of morphisms of C, which go from C to 1 is a singleton. So for every object C, the set of morphisms from C into the terminal object there's only one of them. There's a unique morphism in that set. Cool. I think that's all I had to say about limits. Yeah, I should get on to the next thing. I'll just say a couple of things out loud rather than actually write them down. So the first is, I only defined limits here, but there's a dual notion of colimits. And the idea with colimits is it's essentially the same definition except for the fact that the maps... Oh, I just noticed that those pi's are meant to be alphas, aren't they? But anyway, the maps alpha x and alpha y, for example, are reversed. So instead of morphisms going from C into the diagram, it's morphisms to go from the diagram out to C. The other thing that's worth mentioning is if you want to check that a category has all finite limits, which we do if we need to show if something's a topos, it turns out that it suffices to just check that it has either all pullbacks and a terminal object, that will imply all finite limits, or you can check that it has all binary products, all equalizers, and a terminal object. That will again imply that it has all finite limits. So in practice, we don't need to check every diagram. Cool. Okay. So that's 1/3 of the definition of a topos knocked out of the way. The next part is the bit about Cartesian closed. So to talk about Cartesian closed categories, we have to talk about exponentials. Actually, let's write. So let C be a category. With all binary products. And also, I suppose, actually no, I'll write that in the definition. Let X in C. We say C has exponentials for X if there exists a family of objects denoted by z to the power of x, and that's for any z in C, such that there exist natural by, or actually let's just write bijections for now. And the bijections go between two Hom sets. So the first is Hom C of morphisms out of the product into Z. And the second set is morphisms out of just Y going into Z to the X. And finally, we need to assert also that these bijections are natural in Y. Okay. Let's continue on this board for a second. So the motivating example is once again the category of sets in which I could just tell you what the set Z to the X has to be, but or I could just tell you what it is, but instead it's much more illuminating, I think, to see what it has to be. So what is the set Z to the X? Well, just by properties of the category of sets, this is in bijection with morphisms out of the terminal object into Z to the X. Oh, also aside, the terminal object is just the singleton. So this bijection holds because for each element in Z to the X, there is a map which sends the lone point in 1 to that object. So these sets are in bijection. But then by this above property, we must have Hom C 1 times X to Z, which by properties of the singleton, well, clearly the singleton cross anything is just in bijection with X. So this is therefore XZ. And so that's what Z to the X has to be defined as. So then what are the family of natural bijections? Well, think about what the left-hand side is here. It's a function of two variables that goes into Z. And the thing on the right-hand side here is a function that just goes out of Y, and it maps it to a new function that goes out of X into Z. So then that process is exactly what computer scientists call currying. It's turning a function in two variables into a function in one variable that takes in another input. So x, y, z of f is equal to f bar. Well, where does f bar go? It goes from y to Hom x, z. And it sends y to the function f blank y.
Sorry, why did you say that zx isomorphic to the set of Hom sets, a set of functions from 1 to zx?
Which one?
The first isomorphism.
Because this is the singleton set, right? So each function that goes from a singleton into some set, z to the x, is going to just pick out one element of z to the x. And so therefore, these guys are in bijection with just elements of z to the x.
That's something that isomorphism doesn't even make sense in the general category, because the left-hand side is an object, the right-hand side is a set, so basically you can only make sense of that in the category of sets. It's worth noting also that James was very careful the way he phrased this definition to have having exponentials as a property and not data, right? If there exists a family of objects such that there exists bijections, so it's a condition, not data.
In the definition of exponential, is that for all y?
Yes, so such a family of bijections will exist for all y and all z. So the definition is exponentials for x, so we're talking about a fixed x, but it only satisfies the criteria that you need if such a bijection exists for all y and z, given that x. And you have to assert also that the bijection is natural in y. And if you turn this thing into a if you turn the right-hand side into a functor, so if you turn this into a functor, then it will also turn out to be natural in z. There's exactly one way to turn it into a functor that keeps naturality in z, but that's not very important.
So I just want to clarify where your universal quantifier is. So you want to say for all objects y, so
Yeah. So we should say it should be like for all y. Well, strictly speaking, for all y and for all z, there should be out there, right? So it should be for all y and all z, there exists a bijection, blah.
Can I just ask something? So then, on your point, are you saying something like there's no way to take a free category or something where I can ensure that there'll be exponentials there? Is that what you mean by there's no, it's not data?
That's an interesting question. I think it's a little bit different from what I was talking about. So a category either has exponentials or not. I mean, the way, I think, well, are you going to make a comment about adjoint functors, James? Because I think that maybe you weren't planning to.
I don't have enough time.
You don't have to, Phil.
Yeah, well, I think that's the biggest thing.
I mean, to actually write down the definition of an exponential, it's way quicker if you know what adjoints are, because then you can just say an exponential for x is a functor blank x, which goes from c to c, such that this functor is right adjoint to the product functor blank times x.
Yeah, I'm just wondering what makes this not data in whatever way it makes it.
Well, the existence of an adjoint is a condition.
Sure.
If it exists, it's unique, so it's sort of data.
Yeah.
But it's important to note that it's just the existence.
Yeah.
Yeah, let's say, so for example, when you give the definition of a topos, you don't assert that part of the data of the topos is the exponential. You just say that it exists. It's almost splitting hairs.
Yes, it's a bit of a pedantic point, I suppose.
What's next? Oh yeah, the code unit. Okay, so 1. So I'm going to equivalently just define it as follows. So maybe I shouldn't actually use the word equivalently yet. You can define a map, which is usually denoted by EV, which stands for evaluation, x, z, which goes from, let me make sure I get it right, so it goes from z to the x, cross x, goes to z, so given by evaluation of x, z is defined as theta x, z to the x, z inverse of the identity map of z to the x. So let's just check that I've not screwed that up. So the identity map from z to x goes from z to x to z to the x, z to the x to z to the x. So it lies in this guy in the specific case where y is z to the x. So therefore, if you take the inverse of this map, it should give you a map from z to the x cross x goes to z, which is exactly what I've said it does. Lemma. There exists an there exists an exponential for x if and only if for all f y times x to z, there exists a unique map, which I'll denote f bar, which goes from y to z to the x, such that the below.
Yeah, I'm a bit worried about
Yeah, but that's dumb. No one would do that. Yeah, okay.
Yeah.
Got there eventually. So if there exists a family of objects z to the x, where z, this is quantified over z. Yeah, I should start with let x in C. So x is fixed. If there exists a family of objects z to the x for all z in C, and of morphisms which go from EV x z goes from z to the x cross x to z, such that the following property is satisfied. So f goes from y times x to z. There exists a unique map that goes, which I'll call f bar, which goes from y to z to the x, such that the diagram is as such. So y that's z, that's f. This map here is f bar times the identity on x. And this map down here, and this set down here is z to the x cross x. And then this is the evaluation. So yeah. Well, I'm also not dumb because this is just the condition so far. I haven't actually stated what it is. Then C has exponentials for x. All right. Proof.
Just a quick question before you dive into the proof.
Mm-hmm.
You've got EV x z,
Mm-hmm.
that x is fixed by the z ranges of all objects. Is
Yes.
that right?
Yeah, that's right. Basically, the definition of exponentials is sort of annoyingly asymmetric, even though it's not. It actually is a lot more symmetric than it appears, because in order to define it, you have to fix an x and then parameterize over the other ones. But if it turns out that your category has exponentials for all x, then these bijections will also be natural in x, for example. So it's sort of the fact that the fact that x is fixed, I feel, is somewhat artificial, right? It's basically you don't have any other way to write it down. Okay. Well. Oh, this is the more annoying direction to prove, though.
Yeah. What should we say? So you can at least write down what it is.
So it needs to go from hom c times x to z. So given that map, send it to the unique f bar that's asserted by the property up there. Yeah, okay. So. Wait, uniqueness doesn't assert that it's injective though, does it? It asserts that it's a function. So the uniqueness condition says that it's a function because there's not two possible candidates for f bar. So it's well defined. Well defined by uniqueness. It's surjective.
I feel like you don't want to hide that diagram.
Surjective. So given f bar, which goes from z y to z the x. We define f is equal to the evaluation composed with f bar times id. Which is clearly going to be equal to, which is clearly going to satisfy the property that we want precisely because that diagram commutes. And then f1 bar is equal to f2 bar. Well, if f1 bar, well then by uniqueness you know that this, since these two legs are the same, this leg must be the same. So therefore f1.
Didn't invoke uniqueness, I just invoked.
Well, surely you do need uniqueness, right? Because otherwise if, oh right, no, of course, because f bar is the one that's unique. Yeah, no, okay, oh, yeah, I see.
Maybe it's easiest to write the calculation. So f1 equals ev blah blah, f1 bar equals ev blah blah, f2 bar.
Yeah. f1 bar times id Well, strictly speaking, that's not actually done because you also have to show naturality.
That's easy. So it's also natural,
Yeah. I'm annoyed because the other direction was way better. That was the only one.
right? I pushed you off what you prepared.
Okay. I should probably stop instead of going on to the thing with...
Do you want to define Cartesian close maybe to finish with? Or?
Yeah, right. I was going to give the non-example of Cartesian close with a billion groups, but I might save that for next week. Okay. So C is Cartesian closed. If it has all binary products a terminal object and all exponentials. Cool. That's the end. Questions?
What's the finite limit? Sorry.
Oh, a finite limit is the limit of a finite diagram. So a finite diagram is one that has a finite number of vertices and a finite number of arrows.
Okay, so both.
So in other words, the category is finite. It's got a finite number of objects. The category J is finite. It's got a finite number of objects and a finite number of morphisms.
Okay.
And then to assert that a category has all finite limits is basically just to say that it has all limits of finite diagrams.
Okay. Thanks.
So when you use the word binary product, does that just mean product as you define it?
Yes. So the more general definition of product is, if you remember, the product was the limit of the diagram that had two vertices.
Yeah.
Well, the general product is just the limit of a diagram that's just got vertices, but possibly infinitely many, but it has no arrows other than identities. So, and by the way, that also says that the terminal object is a special case of a product, right? Because it's the product of the diagram that has no vertices.
Okay.